Okay, section 11.6, video 2. Now let's learn the two tests that are in this section. The first one is called the ratio test. For obvious reasons, you use ratios to do the test. So there are three parts to the ratio test. The setup of every single one is identical. So it's the limit as n approaches infinity of a n plus 1 divided by a n, and then it's the absolute value of that. So it's one term divided by the term before it, or one term under the one after it, whichever way you want to look at it. That's the ratio. an plus 1 divided by an, you apply the absolute value, and then all three pieces of the test are referring to that same limit. So if you find that limit to be less than 1, then you can say your series is absolutely convergent, and therefore, by the previous theorem, it's also convergent. If that limit is greater than 1, or all the way to infinity, then for sure your series is divergent. The only kicker is, if that limit is exactly 1, then you know nothing. The ratio test is inconclusive. You can't say anything about that series being convergent or divergent. So less than 1 converges, greater than 1 diverges. That ratio is the same on all of them, okay? All right, so a note, the third part of that ratio test said that if your limit is 1, then you don't know anything. So here's an example of where that happens. For the series, the piece series 1 over n squared, if you set up that ratio, that'd be 1 over n plus 1 squared, all divided by 1 over n squared. When you set that up, you would have n squared over n plus 1 squared. And when you apply that limit, that would go to 1, so you know nothing. Now, technically, for other reasons, you already know this series is convergent, but the ratio test would not apply in this case. Now, for the other way around, the series of the sum of 1 over n, if you set up that same ratio, you get 1 over n plus 1 divided by 1 over n, which works out to be n over n plus 1, which also goes to 1. That series, we already know because it's the harmonic series, is divergent. So here's two different series, both where the ratio test shows that their limit is 1. One of them converges and one of them diverges. So this is just to show that if your limit is 1 when you set up this test, you can know nothing. So don't assume anything if it's 1. You have to use some other method. So let's look at an example. So let's look at the series n to the n over n factorial. So we have a lot going on here. N raised to the n, so this means 1 to the first, 2 squared, 3 cubed, 4 to the fourth, and so on, divided by n factorial, which remember is the product of that number and all the integers below it. So for example, 4 factorial is 4 times 3 times 2 times 1. So by the nature of these terms, they will always be positive. So there's no need to worry about the absolute value sign. So let's set up the ratio. an plus 1 divided by an. So an plus 1 would be n plus 1 to the n plus 1 over n plus 1 factorial. And then an would be n to the n over n factorial. And remember, when you divide by a fraction, that's the same as multiplying by the reciprocal. So that's why you see times the reciprocal here. Now, if we work that out and simplify it as much as possible, n to the n factorial, pull out one of the n plus 1s from this top here. So n plus 1 times n plus 1 to the n. And then in the bottom, pull out the n plus 1 from the factorial, and you're left with n plus 1 times n factorial. The purpose of rewriting it like this is so that we can see that we can rewrite both of the terms that had the power n plus 1 to the power n and n to the power n can be brought together into one fraction as n plus 1 over n to the power n. Now, you might not recognize this because it's been a long time probably since we talked about it, but that's actually the exact definition of e if you take the limit as n approaches infinity. Now, e itself is greater than 1, Therefore, by the ratio test, this series is divergent. Okay, what happened to the factorial, just in case you didn't notice? This n factorial cancels with the n factorial on the bottom, and the two n plus ones also cancel. So the only thing you have left to evaluate are the two items raised to the power n. Okay, so the ratio test works here, but there's actually an easier method, and that is to test for divergence instead. So an itself is n to the power n over n factorial. And if you set that up, you can see that it's n times n times n times itself n times over n times n minus 1 times n minus 2 and so on, which can be written increasing if that helps you understand. 1 times 2 times 3 and so on. So the point of them writing out the definition of the term an here is to show that this value, this term, will always be greater than or equal to n because the top values are greater than or equal to their corresponding values on the bottom. So since this term an doesn't approach 0, therefore we learned that the test for divergence says that means you know that your series is divergent. So it's a little quicker to do it this way. So as we learn more and more tests, sometimes one might be easier than the other. Okay, the other test is called the root test, which again is named exactly for what it looks like. Instead of setting up a ratio of two values, you're setting up the root of your terms an. Now it's the nth root all the time, and it's always the absolute value of an. So notice all three of these pieces again are the nth root of the absolute value of n. So just like before, if that limit is less than 1, your series is convergent. If that limit is greater than 1, then your series is divergent. And again, if it equals 1, then you know nothing. You don't know if it's convergent, you don't know if it's divergent. It could go either way. Okay, something to notice. If you get a 1 in the ratio test, then it's not worth it to try the root test because you'll get a 1 there as well. And conversely, if you get a 1 for your limit in the root test, you're also going to get a 1 for your limit in the ratio test. So if you're going through your list of tests trying to figure something out and you get a 1 from either one of these tests, you need to skip the other one and try something different like the comparison test or the test for divergence or something like that, like we saw before. There's no point in trying the other one. Okay, an example where we would use the nth root test would be something raised to the power n. So our example is 2n plus 3 over 3n plus 2, all raised to the power n. So of course, taking the nth root of that would be a good thing because the power would go away. So if you take the nth root of the absolute value, well, first off, 2n plus 3 over 3n plus 2 is always going to be positive as long as n is positive, which it is. So there's no need to care about the absolute value. However, taking the nth root of this will completely get rid of your fraction, or I'm sorry, of your exponent n, and only leave you with the fraction 2n plus 3 over 3n plus 2. Now, you guys know from older methods of finding limits that this goes to 2 over 3. You would divide the top and the bottom by n, which is how they get from this first fraction to the second fraction, and see that all you're left with are those leading coefficients, 2 and 3. And because 2/3 as the limit is less than 1, you know that the original series is convergent, or it's absolutely convergent, which means that it's convergent. So that was extremely quick compared to setting up the ratio test on that one. And that is the end of 11.6.